Hey everyone, and welcome. Today we're going to pull back the curtain on something your database does every single millisecond, something absolutely critical, concurrency control. So what really happens when everyone on your app clicks buy at the exact same time? Let's dive in. To really get this, just imagine this scenario. You and your entire team are all in the same Google Sheet, and everyone is trying to type something into cell B2 at the exact same moment. It would be total chaos, right? So, who wins? Whose change actually gets saved? More importantly, how do you stop that cell from just becoming a jumbled, corrupted mess of everyone's changes mashed together? Well, that fundamental problem is exactly what concurrency control is designed to solve. And here's the textbook definition. It's all a balancing act. And, if you're a Go developer, you've definitely run into this with Go routines. How do you get things to run as fast as possible at the same time without creating a mess? Databases face that exact same problem, just on a massive scale. They have to maximize concurrency to keep things speedy, but they have to absolutely guarantee correctness so your data stays sane. All right, so that tees up our first big idea, which really gets into the two main philosophies for handling this chaos. Do you ask for permission before you do something, or do you just do it and ask for forgiveness later? And it really boils down to these two big ideas. On one side, you've got pessimistic locking. That's the ask for permission camp. On the other side is optimistic locking, which is all about asking for forgiveness. Let's break down what that actually means in practice. So, pessimistic locking, this is your cautious friend. It just assumes things are going to go wrong and that conflicts are everywhere. For you Go folks out there, this is basically a sync.mutex. Before any transaction can speak or, write data, it has to grab a lock. Think of it like a talking stick. And while it's holding that stick, nobody else gets to write. It's super safe, but man, it can be slow. And it introduces this nasty problem called a deadlock, where two transactions get stuck waiting for each other forever. Okay, but what is a lock, really? Well, at its core, you've got two main flavors. First is a shared lock, or an S-lock. That's for reading. Think about it. A bunch of people can all be reading the same book in a library at the same time, no problem. Then you have the exclusive lock, or X-lock. That's for writing. Only one person can be scribbling notes in that library book at a time. It has to be exclusive. And this little chart, the lock compatibility matrix, lays it all out beautifully. You can see right here, if transaction 1 holds a shared lock for reading, can transaction 2 also get a read lock? Yep, totally fine. Can it get a write lock? Nope, not a chance. And if transaction 1 holds that big, exclusive write lock, well, nobody else can do anything. It's a total roadblock. All right, now let's flip the coin and talk about optimistic locking. This approach assumes the best. It thinks conflicts are pretty rare. This is like working in Google Docs, right? Everyone just works on their own version of things. Then, when you're ready to save, the system does a quick check and asks, hey, did anyone else mess with this while you were working? If the answer's no, you're golden. Your change goes through. But if someone else did change it, sorry, your transaction gets aborted and you have to try again. It can be blazingly fast if you don't have many conflicts. So you see, it's all about trade-offs. There's no single right answer. It's about picking the right tool for your specific situation. Pessimistic is your go-to for high-contention systems. Think banking, where lots of people are trying to write at once. It's slower, but it's safe. Optimistic shines in low-contention environments, like a blog or a wiki, where most people are just reading. It's way faster, but you do risk what's called starvation, where one poor transaction just keeps getting told to retry over and over and never actually finishes. Okay, but what if I told you there's a way to kind of have your cake and eat it too? That brings us to what is pretty much the modern standard, a concept I like to think of as the database time machine. The absolute magic of this next thing we're going to talk about, multi-version concurrency control, or MVCC, it all comes down to this one beautiful idea. Readers don't block writers, and writers don't block readers. I mean, that's a huge deal for performance. Now, if you've ever used Git, and I'm guessing you have, this is going to make perfect sense. When a transaction starts in an MVCC system, it gets a snapshot of the database at that exact moment in time. It's just like creating a new branch in Git. You can work away on your branch, completely isolated, while other people are merging stuff into main. Then, when you write data, you don't overwrite anything. Instead, you create a brand new version, just like making a new commit. The old version is still there, perfectly preserved. All right, let's pop the hood and see how this actually works. It's surprisingly clever. In an MVCC database, every single row has a couple of hidden columns. You can see here we have xmin and xmax. Xmin is the ID of the transaction that created this version of the row, and xmax is the ID of the transaction that deleted it. So right now, this row was created by transaction 10, and it's still active. Okay, now watch what happens. Transaction 16 comes in and wants to update the price. The database doesn't just erase the old data. No, it marks the old row as expired by setting its xmax to 16. Then it just inserts a brand new version of the row with the new price and sets its xmin to 16. This is the magic. Any transaction that started before number 16 will still see that first row with the old price. For them, it's like a perfect photograph of the database from the past. Okay, so everything we've talked about so far, that's been in the cozy, safe world of a single database. But let's be real, we live in a distributed world now. Our data is spread across servers all over the planet. And for Go developers building these cloud-native services, this is where things get really complex. And going distributed introduces a whole new class of headaches. You've got network latency, messages can take forever to arrive or not arrive at all. You have partial failures, where maybe one server in your cluster just crashes. And the really mind-bending one? There's no such thing as a perfect global clock. Every machine's clock is slightly different, making it almost impossible to know the true order of events. So how do you make sure a transaction is all or nothing when it's spread across all these different machines? Well, you use something called a two-phase commit, and the best way to think about it is a wedding ceremony. In phase 1, the question, a coordinator asks every single database node, are you ready to commit this transaction? Then, in phase 2, the vows. If every single node replied yes, the coordinator says, okay, do it, commit. But if even one node said no or didn't respond, the coordinator shouts abort, and the whole thing is rolled back everywhere. All right, for our last section, we're wading into some deep water. This is a real-world debate that senior engineers grapple with all the time. We're going to talk about a very popular distributed locking mechanism and why it's so controversial. A lot of folks, and maybe you've done this, use Redis for distributed locking. It's super common, but if you're just using one Redis instance, you've just created a huge blinking red single point of failure. If that server goes down, your entire system can just seize up because nothing can get a lock to do its work. So, to fix this, an algorithm called Redlock was created. And the idea is actually pretty simple. It's all about majority rules. Instead of one Redis server, you might have 5. And to get a lock, your client has to successfully acquire it from a majority. So in this case, 3 out of those 5 nodes. This is great for fault tolerance. If 1 or 2 of your Redis nodes crash, the whole system just keeps on chugging along. And that sounds great, right? It gives you high availability. But here's the question a senior engineer has to ask. Is it actually safe? Does it truly, under all possible conditions, guarantee that only one client can hold that lock at a time? And according to some really smart people, like distributed systems expert Martin Kleppman, the answer is a big no. He argues that subtle real-world glitches can totally break it. Imagine this. Your client gets the lock from 3 servers. Great. But then, right after that, your process gets hit with a long pause, maybe a garbage collection cycle. While it's frozen, the lock's short lifetime expires on the Redis servers. A second client comes along, sees the lock is free, and grabs it. Now, when your first client finally wakes up, it still thinks it has the lock. You now have 2 clients who both believe they have exclusive access, and that can lead to some seriously corrupted data. And that really brings us full circle. From the simplest locks to these complex, controversial, distributed algorithms, your database and your systems are constantly making these trade-offs between performance, availability, and correctness. So the question I want to leave you with is this. Now that you've seen what's happening under the hood, are you confident the choices being made are the right ones for your app? Thanks for tuning in.